In this video, we're going to go over some practice problems from our textbook on the material covered this week. So that's going to be sections 2.5 and 2.6. Now, starting with section 2.5 here, for these four problems, we want to determine whether each relation defines a function and give the domain and range. Now, looking at question 22 here, notice we have this set of ordered pairs, and that's exactly what a relation is. A relation is going to be any set of ordered pairs. Now looking at 29 here, this is also a set of ordered pairs. It's just represented in a table. We still have these ordered pairs, X and Y here. These are all of our inputs and all of our output values. And similarly, these two graphs here also represent relations. Every single point on each of these lines is going to be an ordered pair. Okay, so all four of these guys are relations, but we need to figure out if they are also a function. Now, remember the definition of a function is that each input value has only one output value. So each x corresponds to only one y. So let's look at this first relation here. We have this set of ordered pairs. Now our input value is 9 for this first one and our output's 2. The next one, our input's -3 and our output is 5. And notice for this last one, our input is 9 and our output is 2. But going back to this first ordered pair here, we already have this input of 9, which is giving us a different output of 2. So in this case, we have a -2 and a 2, which are two different values, which corresponds to our input value of 9. So this would not be a function. We have two different output values for the same input value. So not a function. We have two different output values or y values for the same input value or x value. So each x value can only correspond to one y. And in this case, we have two different outputs. So this would not be a function, but we can still identify its domain and range. So its domain is going to be the set of all of its input values. So we have actually two different input values, just -3 and 9. So this is our domain, all of our input values or all of our x values. And then our range is going to be the set of all of our output values or our y values. So we're going to have -2, 5, and 2. And we do usually like to write these guys in increasing order, but it's not always necessary. Okay, so that's our domain and range for this one. Let's look at 29 here. Now we still have a relation, like I said, this is all of our input and all of our output values. Now notice we have a bunch of different inputs. We don't have any repeated inputs. We have 4 gives us -3, 2 gives us -3, and so on. So in this case, this actually is a function. Even though we have all of these repeated y values here, we don't have any repeated x values. Every single input needs to correspond to only one output, but we can have multiple outputs as long as they don't correspond to a same input value. That was the issue we ran into here. These two y's are different, but it has the same x. So in this case, this is a function. And we'll say each input has only one output. So each input or x value has only one output value. All right, now our domain is going to be the set of all of our x's or all of our input values. And writing this in increasing order, it's going to be -2, 0, 2, and 4. And then the range is going to be the set of all of our output values. Now notice our only output value is -3. So our range is just going to look like this here. Okay, now if we're getting tripped up on the fact that we still have all of these y's here, but this is still a function, this might become clear when we look at question 46. So before we do that though, let's look at 43. Now we have this graph. Like I said, this is a relation. Every point on this line is a set or is an ordered pair. What we're going to do with graphs to figure out if they are relations is we're going to use our vertical line test. Now remember, each input value needs to have only one output value in order for a relation to be a function. So this means any vertical line drawn through the graph of our function must intersect the graph at only one point in order to be a function. Now, like I said, this is the vertical line test. So what we're going to do is just draw a bunch of vertical lines on this graph here. We want to make sure that each line only intersects our graph at one point. Now notice that is the case here. If we zoom in, each line is only intersecting our graph at one point. And this is because we only have one, sorry, these lines aren't super straight, but vertical lines here, they do need to be straight when we're drawing them, but When we do so, we see that they only intersect our graph at a singular point. This means every single input, every single x value corresponds to only one output value. So in this case, this is a function. So we'll say the vertical line test tells us this is a function. All right, we still want to figure out our domain and range. So again, our domain is going to be the set of all of our input values. Now, notice this graph is going to continue on forever in this direction and this direction. So that means as we continue on here in this direction, all of our x values are going to get smaller and smaller. And as we continue on in this direction, all of these x values are going to get bigger and bigger. So this means actually our domain is going to be all real numbers. It's going to be all of these values as we increase in this direction and this direction, looking at our x-axis. So our domain is going to be from negative infinity up to infinity. These are all real numbers. Now our range, again, is going to be the set of all of our output values. So we're looking now at our y-axis, all of these y values. Now, just like in the case of our domain, since this graph is going on forever in this direction, all of our y values are going to get really, really small. So this means our smallest y value is going to be negative infinity as well. And then as we come up on this graph, notice that our biggest y value is going to be this 4 here. Our graph is not going past this y value of 4. So this means our range is going to be from negative infinity all the way up to, and we're going to assume this is including 4. So we're going to use that bracket there. All right, so that is our domain and range. Let's look at question 46. Now, like I said, hopefully this whole idea of a function will stick when we're looking at this visually. We're again going to use our vertical line test. So we're going to draw a bunch of vertical lines through this graph here. Now notice each vertical line is intersecting this graph at least 2 points here. Every single vertical line that we could possibly draw will intersect this graph at 2 points. And this is because, for example, if we were to look at this x value, this input value, which we're going to say is 6. If we look at this x value, notice our output corresponds to 1, but we have another output that corresponds to 3. So this means for this singular x value, we have two different output values. So this means this is not going to be a function. And that's what this vertical line test tells us. We have two different points of intersection for this vertical line. So this is not a function. So that's what this looks like graphically. This is the same instance that we saw here. This input value of 9 has two different output values. This input value of 6 here has two different output values, 1 and 3. Okay. So we'll say not a function. The vertical line intersects our graph at 2 points. All right, we still want to find our domain and range though. Our domain is going to be the set of all of our input values. So we're looking at all of our x's. Now notice the smallest input value that we're going to have is 3. We're not going to go past this 3 on our x-axis. So this is our smallest value, and we're going to assume we're including that on this graph here. Maybe if there was an open circle here or this line was dashed, we would not include this value. All right, now moving in this direction, our graph is going to continue on forever and ever in this direction. So this means our biggest input value is going to go all the way up to infinity. All right, and then our range, we want to find the set of our input values. So these are all of our y values. Now notice if we continue on in this direction, our y values are going to get smaller and smaller forever as we continue in this direction. And as we continue in this direction, all of our y values are going to get bigger and bigger. So this means our range is going to be from negative infinity up to infinity. We're going to include all real numbers. Okay, so those were some examples on how to figure out if a relation defines a function. Now for this next problem here, we want to determine whether the following relation defines y as a function of x and give its domain. Now notice we have an equation here. This is still going to be a relation. We're still going to have a set of ordered pairs. For every single output value that we get for y, we're going to have a corresponding input value that we have for x. So we want to figure out if this does define y as a function of x, meaning if we're going to get a different y or output value for every input or x value. Now, just looking at this, we know this is going to be the case. no matter what, whatever input value we put in here, we're going to get a corresponding output value. And if we change this input value, we're definitely going to get a different output value. We're not going to get the same value no matter how many different x values we put into this equation here. So this will be a function. We're going to say, yes, this is a function because we're going to get a different output value for each input value. We'll get a different output or y value or each input value or x value. All right. So that's the first part of this question here. Now we want to give its domain. Now, notice we have this square root here. That's going to tell us how we can figure out what the domain is because we can't take the square root of a negative number. So, since we can't take the square root, I'm going to abbreviate this, of a negative number, we know that whatever's under this square root has to be positive. It can't be negative. So this means everything under our square root, which is this expression 4x plus 2, has to be greater than or equal to 0. We can take the square root of 0. So this means that we want to figure out what x values are going to satisfy this inequality here. Whatever x values we get are the ones that can be plugged into this function. Those will be our domain. So let's solve for x in this inequality here. What we're going to do is we're going to subtract 2 on both sides. We're going to get 4x is greater than or equal to negative 2. And lastly, we're going to divide by 4 on both sides of this inequality. We're going to end up with x is greater than or equal to negative 1/2, since negative 2 divided by 4 is 1/2. All right, so this means all of the x values for this function here need to be greater than or equal to negative 1/2. So our domain then, our smallest value is going to be negative 1/2, and we're going to have this bracket here to indicate that we're including this value since we're saying x has to be greater than or equal to negative 1/2. So our smallest value that we can have is negative 1/2. X just has to be greater than this. So we're going to go all the way up to infinity. So that would be our domain for this function. Now in section 2.6, we're looking at function notation. And function notation is used like this here. We have this f of x and this g of x. Now this notation is just another name for our dependent variable y. When we're using our function notation in these functions, all we're doing is emphasizing that this output value, this f of x, depends on whatever we plug in for this x value in this function. And this g of x here, this output, is going to depend on whatever we plug in for these x's in this function. Okay, so it's just a new notation to emphasize that the value of this equation is dependent on our input value. So with that being said, given these two functions, we want to figure out what these values are. So for 5 here, we want to figure out what the value of this function is when x is equal to 0. So what we're going to do then is we're going to plug 0 directly into our function. So if I want to plug 0 into this function, we're going to plug it in wherever we see an x. So we're going to end up with negative 3 times 0 plus 4. Right? That's going to give us 0 plus 4, which is just 4. So this tells us f of 0 is 4. This is how we would write out our answer here. So f of 0 gives us 4. Now let's do the same thing for g of x now. We want to figure out what g of x is going to be if we were to plug in negative 2 into our x wherever we see an x in this function. So g of negative 2 is going to be equal to plugging negative 2 into this function wherever we see an x. Now we do have to be careful of our signs here. This entire thing is negative 2, so this entire thing is going to be plugged into this x. So if this x is being squared, then this entire thing, negative 2, is going to be squared. And we represent that with these parentheses here. So we're going to have this negative right out front because the square is being applied to everything in the parentheses. So this negative is going to hang out here. Then we're going to take negative 2 times negative 2. That's going to give us a positive 4. Now for this next term, we have 4 times -2. This is going to give us a -8. And then we still have this plus 1 out here. So just to really emphasize this, this -2 being squared gives us 4. The reason why we have this negative out front is because of this guy. All right, so this is going to give us a -11. So g of -2 is -11. All right, and then lastly for 24 here, this is the same idea, but instead of plugging a value into our function, we're going to plug this expression into our function. And it's going to be the same process. We're just going to be able to combine like terms and get a different expression. So what I mean is f of x minus 2 means taking that entire expression, x minus 2, and plugging it into our function wherever we see an x. So we're going to have -3 times x minus 2 plus 4. And then from here, we can simplify this. We know that this -3 is going to be distributed to everything in our parentheses here. So that's going to give us a -3x. And then we have -3 times -2. That'll give us a +6. And then we still have this plus 4 here. Now we can simplify this by combining like terms. We still have this -3x, but we're going to end up with a second term plus 10. So our final answer is -3x plus 10. If we were to evaluate our function f of x at this expression, x minus 2, we're going to end up with -3x plus 10. Now, the next several questions are very similar. We want to find these function values at these corresponding input values. Now, in the last example, we figured this out using equations, but in the next two examples, we're going to figure this out using graphs of these functions. So for question 41 here, we want to find f of 2 and f of -1. So looking at this graph here, we're going to plug in 2 for our x value and see what we get for our output value or our y value. Plugging in 2 on this x-axis here, the corresponding output value is then going to be +3. So that's going to look like this point here on our line. Let's do some color coding. So this tells us A, f of 2 is going to be equal to +3. Now let's do the same thing for f of -1. We'll do this one in green. What we're going to do is we're going to plug in -1 on our x-axis and see what we get out. We're going to get out a -3. So it's going to be this point here on our line. Our function evaluated at -1 is going to give us -3. Now doing the same thing for 44 here. What we want to figure out is what f of 2 is. So again, we're going to look at 2 on our x-axis and see what is outputted. In this case, f of 2 is going to give us -2. And that'll be this blue dot here for f of 2. Now for f of -1, we're again going to look at -1 on our x-axis and see what is outputted. In this case, that'll be +4. So that's going to be this guy in green there. So for part B here, f of -1 is going to give us a +4. All right, so for the next example, we're doing something similar, but we're going to be working in the opposite direction. In this case, we're still given this graph here, but what we're given is our function value, and we want to find what x value will correspond to the given function value. So let's stick with our color coding here. For part A, we're told that f of x is equal to 3. So this tells us that our output value is 3, or in other words, our y value is 3. What we want to do is look at this graph here and see what x value corresponds to a y value or an output value of 3. So looking at our output value of 3 here on our y-axis, we want to move over and see what this input value is. In this case, that input value is going to be 2. So x equals 2 for this one. All right, let's look at this next one. For part B, we're told that our output value is -1. So we're going to go to -1 on our y-axis, and that's going to give us an x value of 0. We're not moving in either direction. We're just on this y-axis here. So that's that point there, and our x value in this case is 0. Now, lastly, for part C, we're told that our output value is -3. So we're going to look at -3 on our y-axis. That's going to be this here, and our corresponding input value then is -1. So given by that point there. So in this case, our x value is -1. Now for this next question, we're given this equation and we're told that it defines y as a function of x. So this means for every single input value of x, we're going to get a different output value for y. Now the first thing that we want to do is solve for y in terms of x and write this equation using function notation, so f of x. Then what we want to do is evaluate this function at our input value of 3. So for part A, we're going to solve for y and then write our equation using function notation. So we have our equation is minus 2x plus 5y is equal to 9. So if we want to solve for y, we're going to completely isolate that variable. So the first thing that I'm going to do is add 2x to both sides of this equation. Doing so, we're going to cancel this, and we're just going to be left with 5y on the left-hand side of our equation. Now we're going to have 2x plus 9 here, or we could write this as 9 plus 2x. But since we usually like our equation to be in our point slope form, I'm going to have our variable term come before this constant term. So we'll have 2x plus 9 here. And then lastly, to completely isolate y, we're going to divide by 5 on both sides. This is going to give us y by itself on the left-hand side of our equation. Now on the right-hand side, this 5 is dividing this 2x and this 9. So we're going to end up with 2 over 5x for our first term, plus 9 over 5 for our second. Now lastly, we want to write this using function notation. So in this case, we're just going to replace y with f of x. So f of x is equal to 2 over 5x plus 9 over 5. So again, with function notation here, we're just emphasizing that this equation depends on, this output value depends on whatever we plug in for x. So we replace this y with f of x to write it in function notation. Now for part B, we now want to evaluate this function at x is equal to 3. So to do so, we're going to plug 3 into this equation for x. We're going to have 2 over 5 times 3 plus 9 over 5. This is going to give us 6 over 5 plus 9 over 5, which, since these have a common denominator, we can just add their numerators straight across. This is going to give us 15 over 5, which simplifies to 3. All right, so that's it for that question. And then we move on to our last question in this video here. So we want to graph this function and give its domain and range. The function is -1/4 x plus 1. So we automatically know that this is in point slope form, so we can easily graph this. In this case, our m, our slope, is going to be the coefficient of our x term, so -1/4, and b is equal to 1, which tells us that our y-intercept is going to be the ordered pair 0, 1. So with this information, we can easily graph this function. So our y-intercept is 0, 1. That's going to be our starting point. So 0, 1 is going to be that point there. And we're going to use this slope here to find more points on this line. Now remember, since our slope is rise over run, we're going to go up 1 unit. And then in this case, we're going to go to the left. Our run is going to be 4 units, but we're going to the left to account for this negative. So we're going to go up 1 over 1, 2, 3, 4. That'll be another point on this line. Then we're going to go up 1 and go over 4 more. Now, if we want to continue in this direction, instead of going up 1, we're going to go down 1 to account for that negative, and then we're going to go to the right 4. So we're going to have this point here, and then repeating that process, we're going to have another point there. So we're going to graph this equation by connecting these dots here, and we have this line. All right, and the last thing for this question is we want to give its domain and range. Well, let's look at our domain. This is going to be all of our input values. Since this line is going to continue on forever in this direction and this direction, all of our input values is going to be all real numbers. So our domain is all real numbers, which is going to be given by -infinity up to infinity. Then our range is going to be the set of all of our output values. And just like we saw with the domain, since we're continuing on in this direction and this direction, all of our y values are going to get bigger and bigger over here and smaller in this direction over here, since we continue on forever in both directions. So our range is also going to be all real numbers in this example as well. All right, so that'll be it for this week's video.